All right, so let me remind you where we were in section 4.3 when we left off last time. We had talked about what Riemann sums were, and that they have this arbitrariness and that we had made very specific back in the previous section that was not really necessary. The specificity wasn't necessary. It just made it easier to work with. It talked about taking any height for the rectangle, and then it also talked about letting the rectangles become infinitely narrow. Infinitely narrow. They become infinitely narrow, or you can say they become infinitely many rectangles, either way. And then we had taken a look at the fact that this is actually going to give us exactly the antiderivative between the starting and the ending point of our interval, which is going to give us that actual exact area underneath the curve. And it's related back to what we did with antiderivatives in section 4.1, which is what your gateway will be about. And then we talked about the fact that if we have continuity, we automatically get integrability. So we have the ability to do these antiderivatives, indefinite integrals. I already said that one. So we did this example. We had taken a look at setting up a region, just identifying how sort of the pieces correspond. And we had looked at finding the area under curves for geometrics in a couple of cases. So this one was a geometric. It ended up being a rectangle. This one ended up being a trapezoid, which if you don't want to do it as a trapezoid, you can split it into a rectangle and a triangle. It doesn't matter. Either way will give you the same value. Okay, is that good for everybody for where we were before? So there's a bit more in this section, and it talks about the relationship between kind of the order of things in integrals. So these are definitions of two special definite integrals. One of the definitions, the first one, seems quite obvious. If we take our antiderivative or our definite integral from A to A, that is, we start and we end at the same location, there is no area under the curve. And that should make sense because there's no ability to fit in a rectangle. There's no width of a rectangle. Area is always a two-dimensional object, and this would be a one-dimensional object. It would simply be the height of the curve at that point. That's not got any area because I can't take that times its width. So I get 0. The second one talks about what happens if the limits of integration are switched. So if you notice, if we went from B to A over here instead of from A to B, it's actually the same quantity but the opposite sign. So it kind of makes sense if you think about distances, right? So if we looked at the distance between 2 and 5, we would say that the distance is 3. But if I do 2 minus 5 or 5 minus 2, one of them is positive, one of them is negative. Same thing's happening here, okay? So the order in which the limits of integration occur, if we switch them, we get the negative area of that quantity instead. And the last one, the one that's probably the most useful to us, talks about what happens if you split the integral apart, or the interval, apart. So if we have an integrable function on 3 closed intervals determined by A and B, so it has to be integrable from A to B, and then so if you imagine the way that they're describing it is that, I meant to do this one, that you have, here's A, and here's B, and C is somewhere in between. We've talked about this like when we did intermediate value theorem. We talked about this kind of an idea, that if we go all the way from A to B, and it's integrable, and if it's also integral from A to C, which it automatically would be, and from C to B, that what we could do is we could actually split the integral up. So if I found the area between A and C, and I added it to the area between C and B, it would be the area going all the way from A to C. And sometimes it's much nicer because we don't have some nice formula. It's nicer to actually be able to break it up into pieces. So this allows us to break up the area into pieces and add those two areas together. Much like what we actually kind of did on this one where we said, hey, it's a trapezoid. We could break it up into a rectangle and a triangle and add them together. It's doing the same thing. It's just doing it along the x-axis instead of arbitrarily anywhere on the graph. And then we have just a couple more. These are properties of definite integrals, sort of continued, if you will. So if you have a constant multiplier, just like with derivatives and limits and all the good stuff, with summations as well, you can pull that constant to the front. So k times f of x is the same thing as the k on the outside times the antiderivative of f of x. And then if you have the sum and difference of antiderivatives of definite integrals, you also have the sum separated. And we encountered both of these facts when we looked at antiderivatives back in 4.1. We just didn't have the A and the B on the top, okay, the top and the bottom. We didn't have those limits of integration, but it works the same way. Let me pause while a few of you are still writing. So we're not going to talk exactly in this section about how to find any of these quantities in general. That's actually section 4.4. But what we have the ability to do is we have the ability to take some informational pieces. Namely, they're telling us that the antiderivative from 2 to 4 of x cubed dx is 60. The antiderivative from 2 to 4 of x dx is 6. And the antiderivative from 2 to 4 there's nothing in here. So what do you suppose is understood to be in here when you don't see anything? It is a constant, but a specific one. It's 1. So there is an understood 1 right here. Okay? It's kind of like asking yourself what's the coefficient of x when it's not listed. Well, it's 1x. All right? So what number has to be in there? Well, it has to be a 1. Otherwise, if it were a 0, the dx multiplied by it would go away. Kind of an idea. So there's an understood 1 in there. So the antiderivative from 2 to 4 of 1 dx is equal to 2. So in this section, when you're asked to find something like number 4, they're always giving you preemptive pieces of information that they're going to ask you to use to show it. Okay? You're not finding those pieces, they give you that. In section 4.4, we're going to talk about how we find those pieces as well. So in this section, what we're wanting to utilize is we're wanting to utilize all these properties where we have the ability to separate things as addition and subtraction, where we have the ability to pull numbers out in front, and in a moment where we have the ability to switch limits of integration when necessary. Those are the 3 pieces of information we're going to be utilizing to solve, for example, number 4. So you definitely see some addition and subtraction on number 4, right? Yeah. So what we're going to be doing on these problems is we're going to be separating the addition and subtraction using these properties. So one of the properties says, because it was the property number 2 over here, says that I can separate out each of these pieces. So this is x cubed dx. And then I'm just going to do this a piece at a time to make sure everybody sees all the pieces. You don't have to have all these pieces separated, but I'll show that in a second. And then we have the integral of 8 dx from 2 to 4. Okay, so does that step make sense? Oh, I left off my cubes. I moved too quickly past it. Thank you. Is that okay now? All the pieces? Okay, good. Okay, if you wanted to combine that step with the next step and just put the next step down, you could certainly do that. What you see here is actually there's an x here, but this -3 is like property number 1 here. It's a coefficient multiplier, and you could pull it out in front. So if you happen to notice that when you're separating these pieces, and as you're separating it, you automatically pull out the -3, that would be fine. Okay, so you could do that in the same step and not have written that step before. The first step actually is exactly like I want it, and the reason I say it's exactly like I want it is because it exactly matches one of these here. That's why I want it. I want it to match exactly, and the first one does. So there's nothing else I need to do with the first one. The second one, if I leave it right here, doesn't look exactly like what I have, but if I write it in this form, now it does, right? I have a piece that looks just like that right here. Now the last one also does not. It has an 8 in here, right, instead of a 1. But 8's the same as 8 times 1, agreed? So in very much the same way that I could pull that -3 out, I can also pull the 8 out. And I can leave this either not writing it or writing it as 1 dx if you prefer. So if you see all those pieces, and you can jump from here to here, work-wise and so forth, that's fine. If it helps you to see the in-between step, just show the in-between step. It's not a big deal. It's not going to take you but maybe like 30 seconds longer anyway. So do what you need to do. But the cool thing at this point is that each of these match, right? So this piece, and this piece match the information that I was actually given in this problem. the first pink piece is 60. And then I have minus 3 times whatever the second piece is. The second piece is 6. And the third piece has multiplication by 8 in front. And then it's got the value of 2. So aside from notation, right, understanding the notation, this really isn't calculus. This is arithmetic, right? We separated a bunch of pieces out. We pulled out multiplications. We're substituting some things in. It's college algebra at best with the substitution. And then we're going to multiply and add things together. So I have 60 minus 18 plus 16, which gives me what? 58. So you're not finding things directly at all. You are using properties given and substitution. That's all you're doing in section 4.3. Okay, problem number 5 has some addition subtraction stuff to it. There's something else that we see in problem number 5 that we didn't have to deal with in problem 4. What do you see? Yeah, the limits of integration are reversed. Y'all see that? Okay, so the 4 is on bottom and the 2 is on top, and I need to swap them. And there's a couple of different ways you can do that. If you're using this property very directly, whoops, one more back, 2 more back. Where was it? Yeah, that one. You're going to put the negative out in front, and you're going to leave everything inside the same. And that's fine. You can do that. So as you use that property very directly, you can put the negative out in front. You can change this to 2 to 4, and it's x minus 7. Okay, so far so good? That's the property from a few slides back. Allows me to change the order of the limits of integration. Don't forget the negative out in front now, because it will affect the problem, obviously, right? So as we're separating these pieces, I'm going to be extra careful this time, and I'm actually going to put this in brackets for the moment. Again, if you can avoid all that later because you can keep track of all the pieces, that's great. I don't care. You guys are far enough along in math. You know what you need and what you don't. But for the purposes of us doing it together, I'm going to be really careful that we don't lose anything. So this is 2 to 4, and then I've got the x, I've got my dx, and then I have plus the integral of negative 7 dx. 2 to 4, there we go. So again, being super careful, showing all the pieces just for the purposes in here. And then this negative 7, much like the problem over here with my positive 8, can come out in front and leave me with a 1. So I still have the negative in front in my bracket. I have my integral from 2 to 4 of x dx. And then I have minus 7, and I have the integral from 2 to 4 of 1, or just dx if you prefer. So the negative out here in front has to apply to each of my integrals inside. So you've got to do it at some point. If you want to do it here, you can. If you want to wait and do it at the constants, at the numbers at the end, you can. It doesn't matter. I think at this point I'm going to go ahead and distribute it through to avoid having to write brackets more. But this would be the integral negative on the outside still of the integral from 2 to 4 of x dx. And then I would end up with a positive 7 integral from 2 to 4 of 1 dx. Does that make sense? That negative has to apply to each integral. And then each of those, again, look like something I already have, right? This piece and this piece have values up here. So the integral, the negative stays. The integral from 2 to 4 of x dx is 6. And then I have plus 7. And the integral from 2 to 4 of just dx, or 1 dx, is 2. So I have negative 6 plus 14. And that would give me 8. When it comes to quizzes, you'll have a quiz on this sometime. I think it's next Monday or Wednesday, something like that. I think it's Monday. Let's just check real quick. Yeah, Monday. When it comes to quizzes, you need to show me something in here. Right? I understand as you're doing WebAssign, you don't got to show anything for the most part, unless they do the tutorial ones that you guys love so much, and they make you show all the pieces. With the exception of those, you don't really have to show a whole lot. When you comes to your quiz or your exam, do make sure and show me some of the separations of things. Maybe you don't have every single piece of it that I've just written down. That's fine. But you got to show me that you're using those properties to some degree, okay? Any questions on that? That's all I got today, guys. Isn't that fabulous?